Thank you for your interest in digital reconstruction of composite structures using computed tomography measurements. This effort was conducted under the U.S. Navy's SBIR topic N68335-22-C-0663. Before getting into details of this development and the needs that this technology addresses, please allow us to provide some information about our company and our products. Simmetrix develops software for computer-aided engineering, or CAE applications, such as advanced mesh generation and geometric representations of engineering structures. Over more than 25 years since its founding, Simmetrix was the recipient of 18 Phase 2 SBIR and STTR projects from various agencies. Currently, our software is licensed to over 30 CAE software companies that make use of our functionality in their tool development. The commercialization achievement index of our products has been in the 90th to 95th percentile. The capabilities that are made available to the end users nowadays address simulation needs for structural mechanics, computational fluid dynamics, electromagnetic fields, and heat transfer assessments. To satisfy the different meshing requirements of these analysis types, various geometric and meshing capabilities were developed over the years to support engineering design and analysis community. Our goal is to provide to the end user automatic mesh generation capabilities that shorten modeling development time and allow the analyst to focus on the engineering assessment. These capabilities include automatic surface and volume meshing from computer-aided design or CAD or other geometry modeling formats, boundary layer meshes commonly used in computational fluid dynamics or CFD analysis, mesh adaptivity for evolving geometry problems, parallel meshing for large models, and conversion of 3D image stacks into geometries suitable for mesh generation, which is the topic that is mainly discussed in this presentation. Before we discuss more about our effort to provide efficient modeling capabilities to streamline the reconstruction of a physical structure from using computed tomography measurement, let's lay out Navy's current challenges related to structural integrity assessment of composite materials made rotor components, fabrication variability, and the subsequent operation of these rotor components that might lead to supplementary variability due to different damage initiation and accumulation mechanism creates a large amount of structural assessments on individual assets, which are usually carried out via the Material Review Board or MRB decisional process. The speed, accuracy, and consistency of the structural assessment of an individual asset in its current state is very important for the Navy to have an efficient MRB data-driven decisional process. The software technology that we developed reconstructs the physical asset using a set of computed tomography images, and therefore captures the features of the measured asset like defect population, operational damage, and material system layout. The product of this technology consists in mesh generation capabilities that generate a finite element mesh representation that can be used to define a computational model and assess performance of the asset. The outcome of the MRB decision is very important to the efficient operation of various Navy equipment since composite materials are very common in the fabrication of rotor components. The technology developed under this topic streamlines the data transfer from using computed tomography measurements to an analysis-ready and accurate representation of the asset, and can be used by engineers in charge with durability assessment at maintenance facilities. Since this technology connects non-destructive inspection techniques with engineering analysis, any asset-based digital system development, such as a digital twin or digital thread, is enabled by it. Now, let us provide some details related to this technology. The current durability assessment modeling process uses an as-designed representation of the asset, which does not represent the physical condition of the asset, and this could lead to erroneous MRB decisions. The recent advancements in industry using computed tomography makes it now possible to non-destructively identify the state of the asset by disclosing manufacturing defects or deviations from the nominal design and deformations and damage induced due to operation of the asset. The digital reconstruction of the asset from the set of images that result from using computed tomography measurement enable us to create an accurate individual representation of the asset in the computational domain. For the rotor samples made available to us to develop this technology, we are able to reconstruct the outer and inner boundary, ply orientation and thickness, manufacturing defects, and develop mesh generation capabilities that allows users to generate a mesh representation of the asset. The reconstruction of the asset benefits from the mature surface and volumetric meshing capabilities and solver connectivity developed at Simmetrix to further enable usage of another mature technology that is used across all industry. Finite element analysis. Using blade samples that we had in our possession, we were able to demonstrate outer and inner cavity boundary reconstruction, identification of ply orientation, analytical reconstruction of the honeycomb structure, and ply-level mesh generation. We believe that development of image-to-finite element model representation technology has the potential to change the entire engineering design and analysis procedures, as well as asset management. Once the mesh that is created based on the reconstruction process using computed tomography images, all the existing capabilities related to progressive damage modeling become available to the end user. We used a generic blade model to provide two examples of remeshing capabilities. One example demonstrates insertion of a delamination within a boundary of a region modeled as a single material system, while the second example shows insertion and remeshing output for a delamination at the boundary of two material systems. Both remeshing processes are automatic and make use of an arbitrary surface shape to define the delamination. Post-processing techniques are also available in Simmetrix software suite to carry a progressive damage assessment solution. It is important to mention that this project made use of samples from a retired blade to develop this technology. Different modeling capabilities were developed in parallel and, depending on their readiness level, are merged to efficiently connect different representations based on feature identification from the using computed tomography images. The table provides a TRL level of different milestones over this 3-year development effort. It is well known that durability assessment of rotor components based on their current integrity state is a difficult task simply because the current state needs to be quantified, and modeling tools need to be available to the end user to accurately reconstruct the physical asset in the computational ready representation. The data-driven representation of the asset in its current state is the key feature of this technology. On the short term, this technology enables engineers to correctly model the specific asset that provides more accurate durability solutions to support MRB decisions. On the long term, the benefits of this technology type as part of a fleet management system such as digital twin or digital thread that links the asset from a manufacturer to a current state at different stages during its operation are limitless. Technology Readiness Level 6 is targeted at the end of Phase 2. To demonstrate this development level, a reconstruction of a limited length, cross-section of rotating component is desired. To our knowledge, there are two program offices that can benefit from this technology, PMA 275 and PMA 261. We are working to identify other programs that can benefit from this effort. Working directly with PMA 275 and PMA 261 durability engineers or engineers at maintenance facilities will be a good transition plan. Another application of this technology is in specimen and subcomponent durability testing. It is worthwhile to mention that this technology matches the Navy's digital engineering and model-based engineering, or MBE, strategy. We will work with primes to see how this technology fits into Navy's MBE development. The commercial market potential for this technology is quite large since composite structures are used across various industries, and it is applicable to precision machined components, or PMC, as well as ceramic matrix composites, or CMC-made components. Many of the components are high risk for failure and expensive, which makes this technology desirable, especially in aerospace industry on both the engine and the frame side. There are two major ways we license our software for those interested in this technology: giving access to functionality to other CAE companies interested in adding these capabilities to their portfolio, and providing an end product that can be used directly by engineers or software developers at original equipment manufacturers or maintenance facilities. This technology can be used in digital twin type of development that is in high demand by different industries because it can create a computational accurate replica of the asset that is tracked during its operation. There are different ways to transition this technology to start making use of it in meaningful structural integrity assessments by the end users. While we can provide access to API functionality to other commercial or non-commercial CAD and CAE software developers or digital twin or digital thread implementations, we can also work with different program offices or primes to understand their needs and continue developing this technology. Working with the computed tomography or CT technology industry is another venue for further development and partnership. The commercial market is also a partnership venue for digital thread or digital twin proprietary development. For any question related to this technology or the overall modeling functionality that we offer, please contact us. Thank you for your time.